Hello everyone. Today we are going to discuss the problem range update queries from CSES problem set. So the problem says that you are given a array of n integers and you have to process q queries of the type of the two type. In the first one we will be given a, b and u, that denotes that we have to increase all the values having indexes between a to b by u. And second query is that we have to find what is the current value at a position k. So for solving this problem, we have to use segment tree here because all the range related problems can be solved using segment tree only. You must have knowledge of segment tree and a lazy propagation of segment tree here. I will show you how the lazy propagation of segment tree works. So first, you should know how the segment tree is constructed. Suppose we have n is equal to 8, so there will be a node here which will carry sum from 0 to n minus 1, that is 0 to 7. So this will carry sum from 0 to 7. So it will have two children. One will carry sum from 0 to mid, that is 0 to 4. 7 by 3 is 2. 7 by 2 is 3. So it will carry sum from 0 to 3, and the next will carry mid plus 1 to r, that is 4 to 7. Now again this will be break into 2 from L to mid and mid plus 1 to r, that is it will go from 0 to 1, and this will go from 2 to 3. Now again this will break into 2. This will go from 0 to 0, and this will go from 1 to 1. Similarly for this will go from 2 to 2, and this will go from 3 to 3. Similarly for this one, it will be like this. We will go here because of space constraint. It will go into, that is 4 to 5, and next will go from 6 to 7. Again this will break into 2. One will go from 4 to 4, and other will go from 5 to 5. Similarly for this also, it will go from 6 to 6, and other will go from 7 to 7. Right. So what the current node says, that it says that I have all the sum from indices 0 to 7. We know that for a leaf node it just show what is the value of a single vertex or single integer, we can say. So value of 0 to 0 for this test case, it will be 3. 1 to 1 it is 2. 2 to 2 it is 4. 3 to 3 it is 5. Similarly it is 1, 1, 5 and 3. Right. So this node will have sum of its left subtree and right subtree. That is, it will have sum equal to 5. This will have sum equal to 9. This will have sum equal to 14. This will have some 2, this will have some 8, this will have some 10, and 10 plus 10 plus what is this? 14. 10 plus 14, this should have some 24. See also this sum is 24. 5 plus 1, 9 plus 5, 14 plus 2, 16 plus 8, 24. So this is our construction of segment tree. For construction of segment tree, you should know the basic code that is followed all the time. Now we have to update all the ranges from A to B by U. There are two type of updates in the segment tree. One is point update and another is uh, range update. So for point update, what you gonna have to do? You have to just traverse a following particular path which is going to update. Just say we are updating the point 3. So what we will do, we will just traverse through one path which includes the vertices 3 and increase its value. Like if 5 is updated to 7, then this should be increased to 7. Now when we backtrack to this node of its parent, it will just have value of sum of its left and right, so it will be also increased by 4 plus this value. This will be get updated to 7. Similarly, all the vertices having its path and which have 3 indices included in its range will get updated. This is just a point update of segment tree, and another is range update which we have to use in this particular question. So for range update, suppose we have to increase all the values having indices between 3 to 4 or 3 to 5. So we have to make another vector which will store lazy propagation, or which will store what's the amount of value we have to increase. Suppose we are, what we will do, now we have to increase a value of all the nodes which have indices from 3 to 5. We will start at the root node. We will see whether 3 to 5 is included or it is partially overlap or not. We can see that it is partially overlapping. So what we'll do, we will go to its left subtree and we will go to its right subtree. All right. So 3 to 5 is also partial overlapping. We will also go to its right subtree. We will not go to its left subtree because there is no overlap, right? So in this 2 comma 3, there is again a partial overlap. We will go to its right subtree. There is no point of going to its left subtree. So now here we see that we have to update this particular node to, suppose we have to increase its value by 2. This is our m. So this 5 will get increased to 7, right? Now in the right subtree, 4 to 7 is also not wholly included. We will go to its tree, that is left subtree. We will not go to its right subtree. Now here comes the main logic or main intuition behind the lazy propagation of segment tree. See, 4 and 5 is completely included in our range, that is we have to update 3 to 5. So what will we be doing here? It will have another uh, memory with itself which denotes that what particular value we have to increase. Now we have to increase value 2 here. So what we will do, it's contain all the sum from 4 to 5. We will not go further here. We will just update this value to 2 plus what's the number of indices it is containing, 4 to 5, that is 5 minus 4 plus 1 into the value which we are increasing, it is 2. So this value will get updated and we will backtrack from this node. But before backtracking, what will we be doing? We will just say that okay, we have done all the updation from till this point. We will not go forward, but if in future we go beyond this point, we have to increase its left subtree and right subtree's value by 2. In other words, what I am trying to tell you that this is our lazy propagation vector. Here we will store this value 2 and this value 2 in this particular another memory which we are requiring, right? So whenever we again traverse to 4 4 or 5 5, we will first increase its value which the lazy propagation have, and then we will do whatever we have to do. Okay, just uh, erase what I have done. So we will go with our given example. What our example is given? This is our sum from 0 to 7. Now the first query is of type 2. It will go to the indices 3. So it will go here, it will go to then here, because when it will go to right and go to left from here, it will return 0 because there is no overlap. Here there is partial overlap, that's why it is traversing this particular point. And when it will reach this particular point, it will return 5. Okay, this is the first query. Now we are having a updation query and we are updating all the values from indices 1 to 4 by 1. So we will start from the root itself, 0 to 7. We have to increase from 1 to 4 by 1. It is partial overlap. We will go to left, we will go to right. Again, it is partial overlap. We will go to left. Here is, we will go to right. Sorry, 0 to 3. Yeah, we will go to left, we will go to right. It will backtrack from here because there is no overlap. We will update this particular value by 1, so it will be 3. See here, it's a leaf node, so we can't do lazy propagation here, because when we were having completely overlap at this particular point in our previous example, we were stopping at this particular point and then uh, giving the particular lazy propagation value to its children, but there is no children's here of the lead node, so there is no point of giving lazy propagation value to its children. So we just increase its value and then similarly do for here. See, 2 to 3 is completely included, so we will be doing lazy propagation. So here the children's will have its own memory, and this will include the value 1, and we will include this increase this value by 1, so it will be 10. Again we will come here, then we will come here, and then we will come here. It was 1, then we will increase this value, it's 2. So after updation, the next query is finding the value at index 3. So for finding the value at index 3, we just travel the tree. We will go here, then here. See, when we will go to add particular index, we will just add what array propagation value we have to add at every time. We will just see, we were having 1 here, so whatever value we are having, we will just update this value, so it will be become 6 instead of 5. So we will return 6. I will show you my code so that you will get better understanding what I am trying to tell you. This is the accepted code. So there are three functions. First, I have taken an input NNQ, then created a vector and created two vectors. First is the segmentary, which will just contain all the sum from indices L to R, and then created a lazy propagation that I just told earlier, that will be extra memory, which will be storing what particular amount of value we have to increase when we will traverse a particular node. Then I have called a segmentary function. We will just construct a segmentary. Here, what we are doing, we will just start the recursion from 0 to n minus 1, and then when we will be at a leaf node, we will just assign the values which will be initially containing in the given array, and then we will be calculating the mid and recursively calculate the left subtree value and right subtree value, and then just add. This is the basic segmentary code that everyone must know. After the construction of segmentary, we have to run the queries. So we will take X as a query. If query is type of 1, so we have to update all the values from a minus 1 to b minus 1. So in this update function, what I am going to do, firstly, I am so segmentary SG is the vector which will be storing sum from L to R, and LP is storing what values we have to increase in our particular segmentary. That is means which we haven't reached to this particular point, and we have to increase that particular amount of value in our segmentary. So what we will do, we will just find how many numbers are there in the current node, and then we will add all the values that we have to add, and then we will find if it is a leaf node or not. If it's not a leaf node, then we have to add this particular, one second, what I have done here. Yeah, so if the current index is not a leaf node, so we have to carry that particular LP value to its children, and as we have increased the particular value of LP, that is lazy propagation, so we will just clear the lazy propagation. We will find if it is no overlap, then we will return. If it is completely overlap, then what we will do, what then we will add the segmentary value, the incrementing value to the segmentary, and we will find if it is leaf node or not. If it's not a leaf node, then we will again increase the incrementing value to its children's, and again we will find the mid value and propagates recursively. And if the query is of type 2, means if we want to get the value of the k minus 1th index, then what we have to do, simply we have to traverse through each index which contains the range having indices k. Firstly, if this particular code will remain same, because at every time we have to increase its value which we haven't increased before. Like what we are going what we are doing, see, in the updation part we reach only this till this point only, and we say that we will not go further. We will just say that in future if we go further downwards, then we have to increase the children's value by 1. So after fine after that particular updation, when we were going to call the function to get val, when we were traversing this particular point, we find whether there is particular value that we have to add before returning the particular value. We find that yes, there was a value 1 which we have to add, and then we will return. So the same thing we are doing here. We are just adding what we have to add, and then we are recursively calling the function and then returning what the particular value of the node is. So this was the full explanation of the code. I hope you like it. Thank you.